Alright, let's take a look at lesson 8.4, which introduces us to trigonometry, and we'll talk about what that term means in this video. But this is a follow-up to the exploration you did in class, where you took the measurements of the triangles and you tried to look at those ratios by comparing their side lengths. And so we will understand some of the terminology, but we're going to kind of confirm what we know here. In the exploration, you dealt mainly with the special right triangles, but trigonometry works on, or basic trigonometry works on any right triangle, as you'll see in this lesson. Previously, we've used Pythagorean theorem to find missing lengths in a right triangle, but we always had to know two of the three. Well, now I'm going to show you how to be able to use trigonometry in your calculator, and we'll eventually be able to find those side lengths given less information about that triangle, like only one side and the angle measure. We still should be able to find that missing measurement. We'll also use trigonometric ratios to find angle measures in right triangles. We'll talk about how to do that as well. So here's what trigonometry is. It's a study of triangle measures. And in right triangle, trigonometry is called basic trig, and we will abbreviate that as trig. It just shortens it a lot. So in all of these ratios we talk about, we're going to have a reference angle. It has to be one of the two acute angles in the right triangle, and so this would be our reference angle that we've marked in this picture. Okay, I could have just as easily marked this one instead, but we're going to call it angle X. We're going to use this angle measure as our reference angle. Okay? And then we should be able to talk about these sides in terms of whether they are adjacent to that reference angle, opposite from that reference angle, or the hypotenuse, which is always the same no matter which of these acute angles you make the reference angle. The hypotenuse stays the side that is opposite the right angle. So for our opposite side, it's the side, or the leg rather, that is directly across from the reference angle. So this would be our opposite leg, or opposite side. The adjacent side is the leg next to the reference angle, and it's a side of that angle. So this is the hypotenuse, so this would be our adjacent leg. And then lastly, we have our hypotenuse. Is always across from the right angle, so that's your hypotenuse. It's always the longest side. Okay, so that's how we classify sides of a right triangle, as either the opposite leg, adjacent leg, or hypotenuse. We will use these letters, O for opposite, A for adjacent, H for hypotenuse, in the next part of our lesson, so make sure we remember that. Alright, so in this quick example, DE is a midsegment of trapezoid BCGF. Since a midsegment is marked in DE, and then this is a trapezoid BCGF, we know that DE is parallel to both of those segments. And what that tells you in terms of this triangle is that these three segments are all parallel, which makes all of these right angles, as long as one of them is. And then we have three nested triangles. Nested just means we have one within another within another. And they all share angle A, and so when it says justify why the three nested triangles are similar, they're wanting you to pick one of these reasons. Well, look here, they all share angle A, and they all have right angles. So we can make the easiest justification for why these are similar by using angle-angle similarity, because of the right angles, and angle A is congruent to itself. So all these are similar by angle-angle similarity. That means their sides are proportional. So we're going to go back to talking about our similarity of triangles, and we're going to write that similarity statement. We're going to say triangle ABC is similar to triangle ADE, and those are similar to triangle AFG. Now, I want you to think about why I wrote these in this order. You should remember that corresponding parts of similar triangles must line up in this label. So if I said AB as the first segment, in my other triangle I want to talk about the side that is corresponding to that. Okay? That would be AD. And then in the third triangle that would be AF. So I'm going to put those letters in that order. Alright, so we need to show an extended proportion of the numerical measures for the three triangles using the sides. Now they use words opposite, hypotenuse, and adjacent, and so we need to have a reference angle. Since all three triangles share angle A, we're going to make that our reference angle. Okay, so if A is our reference angle, the ratio of opposite over hypotenuse for all three triangles should be this. Let's start with the smaller one since we started with that one in our statement here. The opposite leg from angle A is BC, which is 3, over the hypotenuse. Well, the hypotenuse of triangle ABC measures 5. Now, that should be proportional, or that ratio should be equal to the corresponding ratio from triangle ADE. Well, I need to find the length of the hypotenuse of DE and this segment. Now remember, mid-segments are the average of the two bases. So I just need to add 3 plus 6 and divide by 2. So that's what DE will equal. 3 plus 6 is 9. 9 divided by 2 is 4.5. So the opposite leg of ADE, of angle A anyway, is 4.5 in length. And then the hypotenuse is 5 plus whatever BD is. Well, AF is 10, and this is 5, so BE has to be 5. And BD and DF should be congruent parts of 5, so those are each 2.5. Okay, so the length of AD is 5 plus 2.5, or 2.5, and you get 7.5. And that ratio should be the same as the opposite leg of triangle AFG from angle A, which is 6, over the hypotenuse, which is a total of 10. Well, we know 6 over 10 is the same as 3 over 5. If you wanted to reduce 4.5 over 7.5, you would get the same thing. Okay, you could just as easily multiply both of these by 2 and get 9 over 15. If I divide each of these by 3, I get that ratio. So those are all equal. I want you guys to try and do the adjacent over hypotenuse ratio for all three and the opposite over adjacent for all three. We should have most of our measurements, but you'll need to find CE and EG. But remember, this is 4, so the remaining part, CG, should be 4, which makes the rest of these 2. Alright, pause the video to give yourself enough time to come up with these ratios, but you want a ratio written out like this for the next two parts. Alright, if you need to pause the video to give yourself more time, go ahead and do so. Otherwise, these are what we should get. For the adjacent leg over hypotenuse ratio, the adjacent leg would be 4. Remember, our reference angle is still A. And the hypotenuse is 5 still. So we get 4 over 5. And then for the next triangle, that would be 6, the adjacent leg, 4 plus this 2, over the opposite leg, 4.5. 6 over 7.5 then. Over the hypotenuse, 7.5. And then the adjacent leg, 8 over the hypotenuse, 10. Okay, and again, these all would be the same. 6 over 7.5 is the same as 12 over 15, which does reduce to 4 over 5. And then lastly, we have the ratio opposite over adjacent, and that's where we're going to take the opposite leg lengths and compare those to the adjacent leg lengths. So going back, our opposite first time around was 3, our adjacent was 4, so we get 3 over 4. Then we had 4.5 over 7.5. Over 6. Looking at the wrong part. 4.5 over 6, and then 6 over 8. And so we get those ratios. Alright, we are going to be able to use these ratios. These ratios have special names in our right triangles, and that is the basis for trigonometry, and that is going to come from this key concept. Alright, and these are our trigonometric ratios, or in other words, we'll just say trig ratios. Right? The first one is pronounced sine. Okay? It's pronounced like the word S-I-G-N, sine. Alright, but we spell it S-I-N-E. The sine of angle A, and again, remember this represents a ratio. The sine of your reference angle A, written S-I-N-A, we get rid of the E to abbreviate that, not sin. Sine A is the ratio of the length of the leg that is opposite over the hypotenuse. So like we just talked about when we found opposite of our hypotenuse, these ratios are all representing the sine of angle A, the sine ratio for angle A. Okay, and so in triangle ABC, the opposite leg over the hypotenuse would give us our sine of angle A. Then we have the trig ratio pronounced cosine, co and then sine. The cosine of angle A is the ratio of the adjacent leg over the hypotenuse. So that's that second set of ratios we just found, adjacent over hypotenuse. Okay, the adjacent leg to angle A is this segment over our hypotenuse. And then lastly, we have what's called the tangent ratio. Okay, the tangent ratio compares the length of the opposite leg over the adjacent leg. A tangent does not use the hypotenuse. Okay, so the leg opposite angle A divided by the length of the leg that is adjacent to angle A. Okay, so if we look at those, the leg opposite angle A is called this lowercase a. The length adjacent to angle A is this lowercase b, and the length the hypotenuse is this c. So that's why sine of A is A over c, but sine of angle B, if I change the reference angle, that's B over c. Okay, and then we have these ratios here, but there's a trick to remembering this. Okay, and here is how we can remember this using the acronym, and we actually pronounced this out as we were reading it, SOHCAHTOA. And I know it sounds kind of goofy right now, but we're going to use SOHCAHTOA to help us remember what these ratios actually are when we represent them. So we're going to write these out in words, and I'll tell you what to fill in just a second. But for our calculator use, we use the truncated, which just means we only use the first three letters of sine, cosine, and tangent. We don't say sin, cos, tan. We say sine, cosine, and tangent. Even though we're abbreviating the writing, we can still say the full word. So here's what these letters represent. The sine of angle A is equal to the opposite leg over the hypotenuse. So sine is opposite over hypotenuse. Cosine of angle A is the ratio, the adjacent leg over the hypotenuse. So cosine is adjacent over hypotenuse. And the tangent ratio of angle A is equal to the opposite leg over the adjacent leg. And all this does is help you set up the fraction to be able to talk about those ratios. Remember, these are ratios, and so for the most part, we'll be dealing with decimal answers. Okay, so you can remember SOHCAHTOA. SOHCAHTOA helps you remember how to set up each of these ratios. So here are our trigonometry procedures. Step one is to identify the two sides that you need. Either we are given one and finding the other, or we're finding one given the other. So either at opposite, adjacent, or hypotenuse, and we can label them with O, A, and H. Okay? So here's our first example. If I want the sine of angle T, that's your reference angle, that's opposite over hypotenuse if you remember from SOHCAHTOA. And so I'm going to have us find the ratio of the opposite leg length, which is 7, over the hypotenuse, which is 25. So that's how we get 7 over 25, and you can leave it written as a fraction or you can write it as a decimal. So I'd like for you to find these ratios written as fractions. Alright, here's what you should get. For angle T, the cosine of T is adjacent over hypotenuse, so 24 over 25, but then we change to angle C. The sine of angle C, the opposite leg of C is now the 24, hypotenuse is still 25, and the opposite and adjacent ratio for tangent is 24 over 7. Alright, this concludes part 1 of the notes. We will finish up with these in class and in the next video.